nothing as some duality between gauge theories and string theories. So the first thing we saw was we just drew diagrams. We just started drawing Feynman diagrams, like large N Feynman diagrams. And we saw that large N Feynman diagrams organize themselves by topology pretty much like a string does. So we have a sum of diagrams that can be drawn on a sphere, plus torus with two holes, and so on. And we saw that many features of string theory, like the fact that strings are approximately free, then their interactions cost some power of G string, and so on. Most of the cartoonish features of string theory are also contained in when you study correlation functions of a theory with a large N limit. So this was some hint that there should be some duality between string theory and large N Yang-Mills theories. The other hint of a duality between gauge theories and gravity theories comes from the fact that strings, often, it's up to us whether to think of some process in string theory as an open string or a closed string process. The same things we can often describe either in terms using words of closed strings, like saying a string was going, like visiting grandma, and in the process she got hit by many closed strings. Like, that's a story. And another story is the string was passing by, the string interacted with the brain, became an open string, and this open string propagates and then flies away again as a closed string. And both descriptions are good. Both descriptions are fine. And therefore we have this alternative description. Sometimes we can use just closed strings like gravitons and so on. And sometimes open strings like gluons and heavier modes. So this also hints that there should be some kind of duality between gauge and gravity theories, which is also good. We also said that if we were powerful enough to resum all these interactions with the brain, all these holes here, and resum them all, well, then it will in practice generate some effective background where the string will propagate. And all these cartoons, they become slightly more, they make contact with part one of large N Feynman diagrams very straightforwardly. For example, this is the simplest diagram, just a loop of propagator. And here's a double line. And in this double line, we can interpret as saying that there is an open string here that is going around in a circle, and its endpoints, one of the endpoints is in brain number I, and one is in brain number J. Or we can say that no, instead, we had a closed string in brain I that was emitted and absorbed by brain number J, depending on which direction we see this, we choose to think of this picture. Okay, at large N, so people ask me whether it made any difference to consider UN or SUN. And there should not be any particular difference, right? Because at large N, the difference between SUN and UN is just a U1, some simple U1 degree of freedom. It's much smaller than the huge number of degrees of freedom in SUN or UN, right? Which is a huge group. And physically, the way to think about this difference between UN and SUN is also very intuitive. You see that here you have a stack of brains. And when you have a stack of brains, the string can end on brain I or on brain J, right? And why are these guys massless, for example? Because the brains are all on the same position, so they don't have to stretch. So if the brains were opened up, for example, they would not be, they would have some mass, they would acquire some mass, these open strings, because they would be stretched between brain I and brain J. But they are all at the same position, and therefore, because of that, these excitations are massless, and they are gluons, the lowest energy ones. Now, what happens if we move the stack of brains, all the brains at the same time? Well, nothing special, right? So there should be some U1 degree of freedom that is not very relevant in this discussion. That U1 is the difference between SUN and UN. So you see, it really is not very important. Okay, very good. So before I start, I would like to start with a puzzle or paradox or whatever you want to call it, which we will solve by the end of the lecture, or maybe in half an hour or 1 hour. Which is the following. So let's start with a small puzzle or confusion that comes when we try to mix those two together. So let's say a small puzzle.
One simple question.
There is a question. Good.
In the figure, like when you resum all the diagram, it has only one hole. But when we resum it, do we have to sum over all different diagrams with different channels?
Yeah. Let me Yeah, let's not try to be confusing. So let me put a hole here also and remove this one. So for each, yeah, so the string that is moving on this background itself can then also have holes and so on. That is not related to the interaction to the brain. So that hole remains on both sides, okay? Okay, good. So now here is a small puzzle. So let's go back to our quark anti-quark potential. So here is a quark, and as we said, to leading order, the quark just exchanges a gluon. So this is the process to leading order. We can put arrows, but it's the last time I'm putting arrows. From now on, I will not. But just to... Okay, so a quark exchanged a gluon. So this is equivalent to saying that I have a quark, and there was a gluon being exchanged. In double line notation, this is how we draw it. Okay, but then we start drawing more complicated things where the quark exchanges the gluon and the gluon interacts while being exchanged. All right. And we start drawing all these complicated surfaces. Yeah, let's draw something even more complicated. I don't know. You get the idea. It's not important what I'm drawing, but just the idea that we start drawing many, many, many diagrams. And we start summing over all diagrams that can be drawn on a plane. And we want to think of this as becoming a quark and an anti-quark with some string, some open string, right? Some open string, let me draw it in green, some open string between the two, and this is the string worldsheet, the surface that the string draws as it moves in time. So there is a string, and as it moves, it sweeps some surface, and this would be the discretization of this surface. Okay? Now, and there is yet another picture that I want to put here, which gives it a very nice interpretation for this string, which is to say that when we have a quark and an anti-quark, there is a flux tube between them. Right? This is a flux tube. It's a tube of energy, a tube made of gluons. Right? This is what we expect to do, that what holds the quark and anti-quarks together, why we have mesons and why they form, and we don't see them in isolation because there are these tubes of energy. You probably saw this picture of lattice simulations of QCD, and you see these configurations, and you see these tubes of energy, and you stretch them and so on. I don't know. Have you seen it in colloquia and stuff like this? So you have these tubes of energy. That's how we think of why matter forms these baryons and mesons and so on, rather than just free quarks. It's because of these flux tubes that unite things together. Okay, so let me say that this is kind of the toothed picture. So everything is consistent here. So here there is no puzzle. Okay, so this will be like the toothed side of the story. So we have large n looks like a surface looks like a string is like a flux tube, that's all fine. However, on the other hand, we have Faraday. And Faraday would tell us that, well, if the theory is confining, it's all good. But if the theory is like electrodynamics, or if it's a conformal theory, if it's not a confining theory, so let's say, in a conformal field theory, or like QED, like a theory which is not confining, this is not what we draw for the Faraday lines. Instead, what you draw for Faraday lines is something like if you have a charge and another charge, the line that you draw are something much fluffier. It's not something that looks at all like a string. You would draw something like this, right? This would be what you would draw. Okay? And from this point of view, this flux tube doesn't look at all like a thin tube of energy, that doesn't look like a string, and doesn't look like this continuum limit of these Feynman diagrams. Right? So there is some tension here. So we had all these arguments and so on. These are kind of the toothed side of the story. But then, if Faraday was here, he would say, well, but you are crazy. I mean, it doesn't look at all like a string. It's all spread out, and the lines just open and close and so on. Where is the string? Okay? So, naively, you would say that here there is no string picture. Okay? And this is the puzzle. Okay. So, is everyone puzzled?
Sorry, one question.
But don't ask me what the solution to the puzzle is. Yes?
No, just wouldn't that be an indication that SUN and UN are in fact not very trivially related because they differ by an abelian gauge sector? I mean, so if U1 is so special because it's an abelian gauge theory, like then you get...
No, but I meant even if it's non-abelian, but for example, the theory that we are going to come to in the end of today's lecture or in a while is called n equals 4 super Yang-Mills, which is a non-abelian gauge theory, but it's conformal. It doesn't confine. You see, a theory that's conformal doesn't confine, right? When it confines, it's a theory that develops on scale, which is a string tension, and then it can confine. Conformal theories don't confine. In a conformal theory, what's the potential between a quark and an antiquark? A theory is conformal means there is no scale. So the only scale you have is the separation between the quark and antiquark. So in a conformal theory, Coulomb interaction is exact. In a conformal theory, if you have a quark and an antiquark, the potential between the two is 1 over the radius. The only thing that's non-trivial is what function is on top, what number is on top. Is it 1 or some function of the coupling? But from the point of view of dependence on the separation, there's no scale. The only thing you can write for a potential is 1 over the radius. So any conformal field theory, if you take a gauge theory and make it conformal, consider a conformal limit, which is the simplest limit of gauge theory of quantum field theories. These are theories that don't have scale. So these are conformal theories are the simplest quantum field theories, massless theories without any scale generated. You take these conformal theories, there's no scale. The potential in a CFT, the potential between quarks and antiquarks, as I said, it is just some function of the coupling, of the 't Hooft coupling. But from the point of view of R dependence, just 1 over R, whereas in a confining theory, it grows linearly with R, so totally different. So the Faraday lines are something like what I said, and there seems to be no picture for a string. Okay. And this is going to be neatly solved. I will show you, but for now I want to keep it as a puzzle. Okay. Any other questions? Okay. So now we want to be precise and understand these pictures a little bit more precisely. So we will take n D3 branes with n large. Okay? Now we take n planes. So that a D3 brane, I remind you, is an object that lies there in time and has 3 space dimensions, so like our universe. So we put a D3 brane in 10-dimensional superstring. So we take 10-dimensional superstring and put a stack of D3 branes there. Now, why do we want n to be large? Well, we want n to be large for several reasons. One reason is that we want the interactions with this brane to be organized as a string theory with a large n expansion. So right, the open strings in this brane will have a large n expansion because all the diagrams of the open strings interacting with the brane are nothing but 't Hooft diagrams. So I want large n to have a 't Hooft limit. Another reason why I want a large n, I want the stack to be heavy. Because I really want the stack to deform some background. And I want to think in this picture that there is a probe passing by a background. So I want the analog of the proton. Right? So this is the analog of our proton. The analog of the proton, that we want the proton to be heavy. Okay? Good. we ask, so what's the action that describes this configuration? Well, we have the brane degrees of freedom, we have the bulk degrees of freedom, where the brane, so we have some branes here, and this is the bulk outside the brane, and this is the brane. And we have interaction terms that tells us how fields in the bulk, like the graviton that is here, interact with fields on the brane, which are like these open strings on the brane. So the couplings between these fields. Okay? Okay. So what are these various terms? So let's start, say, with let me see, in how much detail do I want to go? Well, let's start with this bulk term. What is this bulk term? This bulk term is 10-dimensional supergravity. These are the massless modes, the low energy, the lowest, leading lowest modes, right? Like the graviton, and then it's supersymmetric partners because the theory is supersymmetric. Okay, so it's like Einstein-Hilbert plus its friends, plus higher derivative interactions, which come about when you integrate out the heavier degrees of freedom. So when you integrate out heavier degrees of freedom and look at low energy, you get operators with more and more derivatives that become more and more irrelevant as you take the infrared limit of your theory. Okay? Is it okay? Okay. Okay. So this thing would be irrelevant operators, a bunch of irrelevant operators. Okay. And so we have something, roughly speaking, like some integral dh square, where we have our metric to be, say, eta plus h. So we have roughly some kinetic term for h, and then some interactions, kappa h dh square plus that. Well, this will be the action describing, say, the gravitons in this bulk region. Okay. What about the brane? What degrees of freedom do we have on the brane? On the brane, we have n equals 4 super Yang-Mills. This is the Yang-Mills theory. But again, it's supersymmetric because it comes from a superstring. So it is this theory called n equals 4 super Yang-Mills. I will tell what it is in a second, sorry. Plus, once more, higher derivative terms, which come from integrating out the massive modes. And this would be, like, for example, you could generate trace f to the 4 with some couplings and so on. And this n equals 4 super Yang-Mills is the reduction to 4 dimensions of 10 dimensions n equals 1 super Yang-Mills, which is the low energy effective action that you get for open superstrings in 10 dimensions. I'm assuming that this probably Davide mentioned roughly, but if not, it's just a known fact that in the low energy limit, remember we discussed what effective actions you get for closed and open strings in the first lecture. And the claim is that the effective actions that you would get in this case would be supergravity plus higher derivatives, n equals 4 super Yang-Mills plus higher derivatives. Okay? This is what you would get if you start with the superstring theory, impose it's a conformal theory, and so on. And this would be the the relevant action that you would find. Okay? Now, what happens now? The claim now is that if you take the, what do you expect if you take the low energy limit now? Now we go here and we take a low energy limit. And the claim is the following, is that two things remain. N equals 4 super Young-Mills and free gravitons. And the reason is simply that all other terms, all other higher derivative and all other irrelevant operators and even the interactions between the bulk and the boundary, all them are given by dimension-full couplings, by irrelevant operators. So these operators have dimension. So when I construct something dimensionless together with what other quantity, the energy that I'm considering, they always give contributions that decay as I lower the energy. So that's the intuition of irrelevant operators. Irrelevant operator, an operator whose coupling is dimension-full, and therefore, to construct something dimensionless, I must put powers of energy over that coupling, and those powers of energy will make such that when the energy is low, those terms become less and less important. Okay? But this is just a complicated way of saying something that we are all familiar with, which is that we can do experiments in the lab, that gravity is a weak force. So if I have a table with some spin experiments, I can ignore gravitons. Okay? They just decouple. So the claim is that they're at low energy. So the conclusion here is that, so here I would say also dimension-full couplings, dimension-full couplings. And all the fact that these couplings are dimension-full, these ones, and these ones, they are such that at low energies, we have Young-Mills plus free gravitons. Which is what we have in a room when we make an experiment. When we make an experiment, we have our system plus the gravitons flying around, which are free and not coupling to our system. The coupling I can ignore completely. Okay?
Do we construct the interaction term?
The interaction term, we could write it down. There is also a way of constructing it. It will have powers of the graviton times F and so on, but they come again with dimension-full parameters, so at low energy they also decouple.
We cannot construct the dimensionless coupling?
No. So the only one we can is the brain one. So because the coupling of Young-Mills is dimensionless, right? As you know, the trace of F squared comes multiplied by a coupling that is dimensionless. Okay? So that's particular to Young-Mills. So the claim is then that if we call this side of the picture here, let's call it A, and this side of the picture, let's call it B, then the claim is that the low energy limit of A is supersymmetric Young-Mills theory, which is N equals 4 super Young-Mills theory in 3 plus 1 dimensions. This is the low energy limit on the brains, plus free supergravity in the bulk. Okay? That's what we see at low energy. Okay? Now, when is this description useful? So this is a useful or reliable description if lambda which would be the string coupling times n, is small. Sorry. Because if it is small, there are few interactions of these brane fields with the brane. So indeed, it's reasonable to just take this description and let it interact a few times with the brane, and I don't need to back react and form a complicated background. So in other words, yeah, the interactions, each hole that I draw in my Feynman diagrams costs me a power of lambda. So if I don't have too many holes, this is a good description. Okay. So again, this is just, it looks complicated, but all I'm saying is that if I have branes, there are open strings there, and the low energy degrees of freedom of open strings are Yang-Mills. And if you have Yang-Mills theory on a table plus gravity, gravity is the weakest force, and it just decouples from Yang-Mills. You can indeed have a tabletop experiment with Yang-Mills and gravity outside. Okay? Yes?
Are we saying that in this limit, these branes are light, they're not back yet, so they're light in low tension?
No, I'm saying it's I don't say it's, I say it's useful, it's better to work in this language. Think again in terms of this proton and electron. Both descriptions are good, but sometimes it's useful to just consider the interactions of the electron with a proton. Sometimes it's useful to resum everything, right? So I can do either A or B. There will be an equality. So either I do A or I do B. But A and B will be useful in different regimes. It's nothing but a statement that super Yang-Mills is perturbative if the coupling is small. Otherwise, it's non-perturbative. It's strongly coupled, and it's hard to analyze. So unless I am at weak coupling in Yang-Mills, okay, this is the low energy limit, but it's a very complicated low energy limit because the theory is strongly coupled.
And in the supergravity action, you don't have any form, I mean, terms correspond, let's say. You do have
not just gravitons, but you have all the kinetic terms of everyone in supergravity, but they are just free. The interactions, the force is weak at long distances, right? Sure. Gravity dies off at long distances, which is low energies. So at low energies, I don't need to consider interaction of gravitons.
So anything which has beam union or anything of that sort will be suppressed in the drawing?
No, there will also be kinetic terms for those, but again, no interactions between, I don't need to consider interactions. Okay? Like here in the room, I don't need to consider cubic interactions of gravitons. I mean, that's super suppressed, right? Gravity is free, and that we don't need gravity to study low energy physics. It just decouples. It's there, of course, but it decouples at low energy. Okay, so now let's think of the point of view B. Okay? So this is A. What about the point of view B? Okay? B. So in B we say, oh, I'll put a brane, I'll put a stack of branes. And I want to ask, what background does it generate? So I put this heavy object, and I ask, what background does it generate? So imagine I put a sphere. What object does it generate? I solve Einstein equations, and I find a black hole. I say, well, it generates a black hole. I put the mass, it generates a black hole, right? If I have Einstein equation sourced by a point like mass, it gives me a black hole. So now what we have to do is take the GR equations which follow from the string effective action that we discussed, which I remind you tells us what backgrounds are good backgrounds in string theory. So we put string theory and so on. And we solve these Einstein equations with a localized source, which is not the point, but the plane. We say we put this plane there, and we solve this Einstein's equations with this source. Right? So what do we do? What do we find? Okay? So we solve, and we find the following metric, the following 10-dimensional metric. Okay? So let me explain. So there is some eta mu nu dx mu dx nu, where these mu and nu directions are the directions in the brain. So these are the directions in the brain that contain time and also the 3 directions in the brain. So mu and nu run from 0, 1, 2, and 3. Okay? I will write something more in this formula. And then there will be also some term dxm, where m is 4 up to 9 are the other directions transverse to the brain. So there are 6 directions transverse to the brain, perpendicular to the brain. And now this should be the form of the metric is where you see this is a function of r, and this here is another function of r, where r is the distance from the brain, r squared is just xm, xm. And you see this ansatz, it had to be of this form. It's just symmetry, right? It only depends on how far you are from the brain, and there is a symmetry bit of rotation of the orthogonal direction, rotation inside the brain. So all you have to do is find this function f and g. That's the only thing you should try to do. So you plug this ansatz with the function f and g into the effective Einstein equations. You solve them and you find what f and g are. Okay? And this is what you get. And the mapping of these parameters is such that when you solve it, that L to the 4 is equal to G Young-Mills square n times 4 pi alpha prime square, where 2 pi probably there is a, okay, I don't know, maybe like, that's probably a square. Okay. It's not in my notes, but if there is a 4 is 2 square, probably the pi is also square. Okay, so where 2 pi alpha prime is the string tension. So, and this is, so when is this solution good? The solution is good, or good in the sense of when is it simpler? It's simpler when the curvature is small, when this solution doesn't have huge curvatures. So the curvature being small means that this L should be very large, such that you need to vary the metric in big distances, small r, to find some difference, right? So small curvatures are large L. So you see that this has small curvatures, which means simplest, for G Young-Mills square n much bigger than 1. Whereas here it was exactly the opposite region. Okay. And this is intuitive. This is just a statement that if I put many d-branes, n is the number of d-branes, then I generate some heavy, good classical background, which means that when n is, that in this limit, when the coupling is large, I do have many interactions, and it's a very good idea to think in terms of the background picture. Whereas when the coupling is very small, I have a very curved background, and then whatever I'll do on top of this curved background will be tricky. But this we will see soon. Okay. So now, let's study a little bit this background. Okay? Let's study this background. So there are two natural things we can do. Okay? So when r goes to infinity, ds squared goes to what? Flat space. We go far away from the brain, we don't see the brain. Nothing special. So we go to ds squared of flat space, that Minkowski flat space. Okay? So this just means you go far away from the brain. Okay? So we get flat space. Okay. What about if we do r going to 0? Well, when we do r going to 0, the metric goes to, and now I will reshuffle a little bit the terms. I will write them like this. R squared over L squared eta mu nu dx nu. Okay? So this is the first term. And now from the second term, I'll go to radial coordinates and write in radial coordinates plus L squared over R squared dr squared plus L squared d omega S5 and the metric of a 5 sphere. Okay? Is it clear what I did here? I just went to radial coordinates and said that I can parameterize R6 by having some origin and then a 5-dimensional sphere. Now it turns out that now if I think of this space here, this part here, you see I take one of the directions from orthogonal to the branes and I keep the spherical part outside. So this is a 5-dimensional sphere. And this is what's called a 5-dimension anti-de Sitter space. Okay, it's a known metric. It will be the subject of tomorrow's tutorial to explore this metric in various details and see what's the physics and the geometry of this metric. So what we get in this limit is the metric for the geometry ADS5 times S5. Okay? Great. So now let's see what happens at low energies. Okay? So now we consider low energy. Okay? But now something very, very interesting happens when we consider low energy in this side that I'm now going to explain. So if we consider low energies, let's see what happens. So let's consider an observer that is here at r equal infinity. And here are two friends. Okay? Here are two friends. And one friend contains, as in his hand, a piece of plutonium. Some big energetic thing. Okay? Or like an atomic bomb, I don't know. It can be an atomic bomb. Okay? So it's carrying something very, very energetic. And then he goes and moves towards the region r equal to 0. Okay? And now let me explain, let me remind you, let me tell you simply that from the point of view of the guy at infinity, if the guy at infinity is looking at what happens, what he will see is that as this one moves to infinity, now it looks like what he has is almost the energy is very, very small. Okay? Whatever he starts with, he takes it inside and his energy is very, very small from the point of view of this guy at infinity. Okay? So this is just standard blue shift or red shift that I will now explain. So let's see. So for r close to 0, we have that ds square is equal. So when r is equal to 0, it will be equal to minus r square over L square dt square plus other terms. Okay? So it means that a proper time, the time measured by the invariant interval, is equal to r over L times delta t. Okay? But okay, delta t, I mean, you should never trust coordinates. Coordinates are not physical, so we always have to give a meaning. This is physics, this is nothing. So let's give a meaning to delta t. What's delta t? So this is the time measured by someone at some radius. So this is time measured by observer at r. What is this? Let's give a physical meaning to this. Very good. This is the time, let's put an infinity, delta t. So this is delta t infinity, is the time measured by observer at infinity. And therefore, by inverting this relation, I conclude that the energy, the proper energy, the energy of the guy close to the brain is L over R, or rather I will put times R over L, is equal to the energy as seen by the observer at infinity. Right? So if you carry a piece of plutonium and you walk with a piece of plutonium close to the brain, of course for you it's always a piece of plutonium, the energy is not changing, it's always the same energy, right? You are just carrying it with you. So this proper energy is still the same, but from the guy at infinity, you see it becomes multiplied by R, which is very small. So as you are approaching the brain, the energy that the guy at infinity sees is becoming redder and redder, and at some point it's just some very, very dim effect. So the observer at infinity, what he would say, let's put some, what he would say is that at low energy, there are two things. So at low energy, he would say there is gravity far away, because he will say where I am, I see a bunch of gravitons. That is far away when I am in flat space here, in this region of flat space. If I want low energy, it must really be low energy, like the gravitons moving around. Plus anything close to the brain. Because anything that's close to the brain for him looks like low energy. For him is low energy. Okay? So the conclusion is that the low energy limit of B is equal to anything close to the brain, so the full quantum theory of everything, which is super strings close to the brain, and the close to the brain is AdS5 times S5. Anything, it can be this atomic bomb, it can be string theory, it can be anything, it can be a black hole close to this region in AdS5 times S5, plus free supergravity, which is at t equal infinity, so decoupled. Right? So this is what you would conclude. And now, what you do is, you say, well, but then you cross this out. And you say that the duality is now a very sharp duality. You say that n equals 4 super Yang-Mills theory in 4 dimensions should be dual, should be the same thing as strings superstring theory in AdS5 times S5. Okay? And this correspondence is from 97, from Maldacena. And the argument I gave you is called Maldacena's decoupling argument. And I personally think it's probably the most important argument in theoretical physics of the past 20 years. But I really think it's something extremely important. And it provides a conjecture, now slightly more than just hand waving, between two theories. Where I can write the Lagrangian of n equals 4 super Young Mills. I can write the Lagrangian, the action for superstring theory in AdS5 times S5. And this correspondence is the simplest realization of what's called an AdS CFT duality. Okay? And why AdS CFT? AdS because there is a background here which you see is anti-de Sitter. And CFT because this theory, n equals 4 super Young Mills, this theory is a CFT, is a conformal field theory. Okay? It's a theory without any scale, and that's why it was important at low energy. We could not drop it. It had no scale. It's definitely something that has massless modes and survives at low energy. And this is a theory. So the beta function is 0, and so on. So it's a conformal field theory. And here is a superstring theory in AdS5 times S5. Okay? So,
Question?
well, one second. Let me just write something. Sorry, well, 1 second. Okay, or ask me, yeah. Who is asking? Yeah.
In this picture here, we had a correspondence between A and B. But B was fully in 10 dimensions, right?
Yes.
And A had a part which was 3 plus 1 dimensional super Young Mills.
Yes.
So where have the other 6 dimensions gone on the left side?
They are not. The duality, yeah, so this is going to be part of the comments. It's totally shocking that you have a duality between a 4-dimensional theory and a 10-dimensional theory. This should indeed come as a shock. So the claim is that we have a theory without gravity, which is n equals 4 super Young Mills. It's just a gauge theory. And it's only in 4 dimensions. And this is equivalent, it's dual, it's the same thing as a theory of everything with gravity, a string theory with everything, gravitons, black holes, quantum gravity, all the quantum gravity effects, and in 10 dimensions.
Does that mean some of the degrees of freedom in the superstring theory aren't really there? Or
No, they are.
are they redundant somehow? I mean, if you can formulate a description in fewer dimensions, then it must be like some redundancy, right?
Well, you are absolutely right that we just conjecture the duality between the theories, so let me just write. So what do we need next? So next, let me just address your question. Next, we need 2 things. 1, a dictionary. Otherwise, it's irrelevant to have a duality, right? A duality is useful if you can translate, if you can exactly explain where are these degrees of freedom, are they one-to-one, do they disappear, or how are they organized, why. If you tell me the theories are dual, it's only useful if I tell you 2 independent recipes for computing the same thing, and then you can go and you have a dictionary. And second, because this was very hand-waving, we need checks. Because this is a conjecture. This was not a derivation. I hope you understood that it's not a theorem. I mean, like, mathematician would not let me go through all these steps, right? I mean, it was kind of hand-waving, trying to say, well, at low energy this, low energy that, this decouples, we take low energy. Then the 2 descriptions are valid a priori in different regimes, one when this is small, one when this is large. We assume there's no phase transition between the 2, and things should be smooth. Then we say, well, it's probably just an equality. It is just that one side is hard when the other one is easy, and vice versa. And we say, okay, let's try. Probably it's true. So Okay? As I said, we will have several arguments for this duality. None of them is perfect. So now, to this list of evidence for this duality, we add a third one, which is a stronger one in my opinion, which is the decoupling argument, which is what we just saw now. As you probably agree, without the previous two it would be harder to digest, but it's definitely the strongest of them. I could have started by this and then have given the other ones, but I think it would have been hard to digest. Okay, so just the simplest part of the dictionary, just to write a few explicit formulae. So, can I write there? Or is it okay if I write there? So, the Lagrangian of n equals 4 super Young-Mills would be equal to 1 over G Young-Mills square and trace over n by n matrices of f mu nu, f mu nu, plus other stuff that maybe I will describe today, maybe not, but it's like Young-Mills plus other stuff that make it supersymmetric. But what I want to point out here is that here are the two numbers, remember, G Young-Mills and n, the size of the matrices and the coupling of the theory, right? So the two relevant couplings are the 't Hooft coupling lambda and n. It's more useful to think in terms of these two rather than G Young-Mills and n, because we saw that lambda is the most relevant one. Whereas the Lagrangian for the string theory in AdS5 times S5, and perhaps it's useful to write the integral of the Lagrangian, which would be the integral of this Lagrangian with some d for x, and this would be the parameters. Whereas the integral of the Lagrangian for string theory, so this would be now an integral over the worldsheet action d to z, so 4-dimensional here and 2-dimensional here. And what you can write is here, you can write G mu nu of x dx, or rather, let me write a b dx a dx b, where this a runs from 0 to 9. And I want to write this, all this, as being dimensionless, which means that I measure things in units of this L there. And L, if you see, it has some pi alpha prime, it has some string tension in it. So when I take out L and I take out L square, it combines with a string tension to give me something dimensionless, because the full action must be dimensionless. And what do I get when I take that L? You see, I need to take L square. So when I take L square, I get exactly outside here square root of the 't Hooft coupling, G Young-Mills square times n, when I take square root of that equation, which is L to the 4. And then there is some 2 pi alpha prime, which is just 1 over the string tension, so it cancels with the string tension. So in string theory, here, this is the dimensionless string tension, which is what makes sense. I mean, in physics, you should not have dimensionful quantities, so it's a dimensionless parameter. So it's either much bigger than 1, much smaller than 1. I mean, it has no dimensions. And there's also n, which is related to the genus. This is the Lagrangian, but then we put this theory on various genus. So n doesn't appear here. N appears when we'll draw the cartoon of the sphere and put this in at various genus G surfaces. And this is the first piece of dictionary. You see, here is one of the couplings, and here is the other coupling. So you also have, of course, a lambda and an n. And this theory here, we have Feynman diagrams, so perturbative quantum field theory for lambda much smaller than 1. And in this picture, we have classical, or simpler, classical string theory for lambda, the string tension, very large. So in that sense, this is a duality. But if you want to compare things in both, you would have to be able to, for example, if you want to, from string theory, reproduce a perturbative result, you have to deal with very fluffy strings fluctuating a lot with some string tension that's very small. And if you want to reproduce from Yang-Mills some classical string computation, just a minimal area between of a string surface, you would have to resum all Feynman diagrams and analytically continue them to strong coupling. So it's kind of a good duality. You conjecture it and then no one can check it because the regimes of validity don't overlap, and when one is easy, the other one is very hard. But of course we can do better than that. Yes? Someone asked something? Yes.
So I read some papers that people had checked at the planar, for planar diagram, we can use some localization technique to check input for square Yang-Mills and compare with the action at the ADS5 and S5. Right? But have they made any progress for non-planar diagram?
Well, they asked me that question at the end because I would have to explain to people what's localization, and that statement is not even correctly really true. So I would have to first correct your statement and then explain what the words mean. So ask me at the end. But it's roughly correct, and then the answer is that beyond the plane, there are not many checks of this duality beyond the planar limit. But there are some very important checks. Okay, so more. Any other questions? Of course, yeah.
When we set up the problem, like n used to be the number of brain we have, and right now it is connected to the number of genus of this string. So how is this connection engineered?
Because n, you remember, was also the let me think how I want to say. So you would agree if I put G string there, right? You would say there is string theory in ADS5 times S5. So I should put G string there, right? Then I have to tell you why G string is related to N. Actually, well, perhaps I should say slightly, yeah, perhaps I should put G string and identify rather G string with G Yang-Mills square, which would be the string coupling. But saying that it's G Yang-Mills square or N, because lambda is fixed, it's just the same, right? Yeah, when you say things are an expansion in powers of G Yang-Mills square, where when you are saying things are expansion in powers 1 over n, because lambda is fixed, it's the same. It is just changing a little bit the variables. So you can think in terms of n, but you can also think in terms of G Yang-Mills square. But the point is that there are two parameters, one that controls the genus, and one that controls the vibrations of the string. Similarly, in Yang-Mills, there are those same two parameters. One that organizes things by genus, and for each genus, one which is a 't Hooft coupling that sums over the triangulations. Okay? So we have the two parameters on both sides. Okay? Okay, so I would like to make now a few comments, and in particular want to come back to this puzzle.
Is the classical string you mentioned there, like are you saying that the string theory in the classical sense, what is classical string? You mean it is not a quantum?
That I'm saying that if the string tension is very large, when you do the path integral, you can just compute saddle point.
Oh.
So But I made a remark in the beginning that we should be careful, because when the tension is very large, two things can happen. If you force the string, then it's just saddle point. If you don't force, the string will rather shrink, and it's a point-like limit. Both cases are a simplification of string theory. Classical strings, perhaps is a word more appropriate to the case when the boundary conditions are forced. Then you just get some minimal string surface. Okay, so some remarks now before addressing the puzzle. Okay. So the first remark is that we use D3s, right? And we could use other heavy string objects, like other branes or more branes, and then repeat the same kind of analysis, right? So in this way, people did. So we can generate in this way, more dualities through this decoupling argument. So in the end, you forget about the argument and just conjecture some duality, and you go and check it. And you can forget about string theory roughly at least for half of the duality. And if you want to see what theories are nice theories that have a dual, this is one way of generating many examples. Okay? So what we said before is that if I give you some theory like Yang-Mills, it's very tough to know what string theory will be the dual. This at least gives you a way of generating many examples. Just start with some heavy object and consider it from 2 points of view, its low energy limit, either from the degrees of freedom on the object or from the background it generates and from the studying the near geometry limit. And if this near geometry has some kind of redshift effect like the one we saw here, you will have some nice duality between string theory and gauge theory. Okay? So that's the first remark. The second remark is that on the S5, we can, if we want, Kaluza-Klein reduce. Whenever you have a compact space, you can decompose into the various harmonics of that space and keep the very first few, right? So if you have a compact sphere, you can say the wave function on the sphere is just constant, or one mode, or two modes. And it costs more and more energy to excite more and more heavier modes in the sphere. So you can, it's equivalent to have a compact space or trade it by many fields, one per each harmonic of the sphere, right? So when we Kaluza-Klein reduce, we could get ADS5 plus with many harmonics, with many fields. So even though it's 10 dimensions, we should distinguish between ADS5, which is a non-compact space, and S5, which is a compact space. Okay? So ADS5, however, we cannot Kaluza-Klein reduce. It's not a compact space, so we cannot just think of it as we must deal with it. So ADS5, we stay. So morally speaking, we have, that's why people say that we have a 4-dimensional gauge theory equal to 5-dimensional gravity. Okay. This seems to be roughly, in this sense. That, okay, it's 5 or 10, it depends, but okay, 5 of them you can Kaluza-Klein compare, but at least 5 you must have. Okay? And this is kind of striking, as we said before. It looks like you have a simpler theory is dual to a richer theory in one more dimension. Right? So there were some hints that something like that had to be true. Indeed, there is another hint of this duality that I will add to this list of evidence or hints for this duality, which is called, we have, holography. holography is the following vague idea. It's a vague idea, but a deep one. It says that, imagine we start throwing stuff inside this room. Lots of stuff, lots of heavy stuff. All right? So lots of very heavy stuff. At some point, you form a black hole. Right? So the idea is that we take some room, we throw in stuff, and time evolves, and now we have a black hole. The black hole entropy is the area of the black hole over 4. So the idea is that this should be the maximum entropy that any system can have. And it should be the maximum because we can always, if it was not the maximum, imagine I have some entropy bigger than that. I throw more stuff, form a black hole, and the entropy would decrease. But the entropy should not decrease, so it better be the maximum. Okay, was it too fast? I will just repeat exactly the same words. Okay? It should be the max because otherwise I can decrease the entropy by adding stuff and forming a black hole. But if this is true, then it's something very deep. It tells us that if you have some volume, some region in the volume, the amount of information contained in this volume should actually be proportional to the area of that volume and not to the volume of that volume. Okay? So this tells us that the idea that somehow the information info in some volume is in the boundary of that volume. And you see, it's a very vague idea. If someone tells you, well, are you after a theory of quantum gravity? Please try to do something. Try to find a theory of quantum gravity where you have a theory of quantum gravity in d dimensions, and this is equivalent to a theory in one less dimension. You should be able to, whatever you describe in these d dimensions, you should be able to consider its boundary and just study the theory in one less dimension. And if someone would give you this as a hint, and then you'd have a piece of paper, I mean, it looks crazy. It looks like it's impossible. How am I going to find some theory, and then the theory has another description in one less dimension? It sounds totally insane. And this is exactly what this ADS-CFT is doing. It's exactly giving us a description of gravity in 5 dimensions in terms of a theory of one less dimension, which, as you will see tomorrow afternoon, and tomorrow I'll also explain, we can indeed think of this as this theory as living in the boundary of this ADS5 times S5 space. So there is indeed some sense in which this n equals 4 super Young-Mills is kind of the boundary, like a surface of a crystal ball, and inside the crystal ball there is quantum gravity. And amazingly, you have quantum gravity inside this crystal ball, and it's described purely by the surface of the ball, which is a theory in one less dimension. But this is just taking to the extreme what this hand-waving argument was indicating. Indeed, whatever theory of quantum gravity you have, it better have this property. And I mean, no one could find any other realization of quantum gravity other than ADS-CFT. I would say ADS-CFT is our best definition of a theory of quantum gravity. And indeed, it realizes very well this intuition of holography that I'm going to add to our list of arguments in favor of these dualities. Yes?
So is it obvious that because the entropy is scaling with the area, that everything that you'd want to calculate in gravitational theory would depend on the boundary?
No, none of these arguments is a theorem, as I said several times. No, it just indicates that it's the information, right? Entropy is the information.
Yeah, but if you're saying that the theories are equivalent, then you would have a lot more quantities that are scaling with the area, not just the entropy, right? Or which depend only on the boundary. Like how do you generalize from this one quantity to entropy?
Yeah, I definitely. I still need to do it, of course. Yeah, we still need to add a dictionary, right? I think this is what you are saying. If you want other quantities, like what quantities do we want to study in gravity, right? So there is also that question. What do we want to study in gravity? One thing is entropy of a black hole. What's the other thing you could study? Well, you cannot study correlation functions because in gravity those are not good observables because as we said, correlation functions at points x don't exist because we sum over metrics, so they can be whatever they want. So these are not good things in quantum gravity. What instead could you do? You could take quantum gravity and scatter stuff, scatter gravitons from minus infinity and receive gravitons at plus infinity. These are good observables in quantum gravity, for example. And indeed, we will see that from that point of view, you can think that you have your crystal ball, and what you are doing is putting some sources, which are like when you emit the gluon, the gravitons. Let the gravitons fly, they interact, they come, and they are received again at the surface. And we would have to come up with a dictionary that I will tell you precisely what's the rule for computing things in the boundary and in the bulk, and then we can compare and see that it works perfectly. But indeed, it's not just the entropy. I need to make a list of everything that is kosher in quantum gravity, everything that's good and proper to compute in quantum gravity, and I should come up with an analog quantity in gauge theory. Right? Of course. I mean, we are just starting to build the duality. You know, Maldacena proposed this duality in 97. Then, for example, in 98, he said, oh, by the way, quark-antiquark potential. Here is how you describe it in gravity. I mean, the people took then a long time to work out a precise dictionary to the various quantities in the gauge theory and in the string theory. And some quantities, the duality between some quantities is still being built right now. Okay? Did I answer your question?
Yeah, I think so.
It is just, yeah, indeed, this is one piece of evidence, but of course it does. I'm not saying that any of these points by itself is enough to be happy. I'm trying to argue that the union of all evidence we have make it very plausible that these dualities hold. So you should really take your favorite piece from each small piece of argument. So now we can go back to our puzzle. And now the solution to the puzzle is actually very simple and cute. Okay? So maybe before that, let me say something more. Let me take this 5-dimensional anti-de Sitter space, and let me do a change of variables where R becomes L squared over Z, such that Z equals 0 now is what was before R equal infinity, and Z equal infinity is what was before R equals 0. Okay? So it's just that after this change of variables, the metric becomes just dx mu dx nu plus dz squared over z squared times L squared, plus the metric of the 5 sphere. But the metric of ADS can be written in this way. Okay, it's just a metric of ADS. So this metric of ADS is very nice to draw. Fix Z. If you fix Z, you have Minkowski. But for various Z, you have Minkowski rescaled by a factor of Z squared. So it's like various foliations of Minkowski. So one way of drawing ADS is of saying that I have Minkowski space, and this is Z. So this is Z equal to 0, which was before R equal infinity, which was going far away from the brane, right? It was the boundary. If you are in ADS and go to R equal infinity, you are leaving ADS. You agree? So this is the boundary of ADS. And at the boundary of ADS, what do you have? You have flat space, R1, 3. So we can say, but with quotation marks, this is where n equals 4 is. It's at the boundary. And then as you increase Z, you have various copies of Minkowski. So we say as we increase Z, we could draw saying that we now have various foliations of Minkowski that are becoming smaller and smaller, and they would increase as you increase Z. Okay? So this is the picture that you have some boundary. It's like the boundary of the crystal ball that I said, and then some bulk. So this is the boundary, and this is the bulk. Okay? And now, we go back to our puzzle. And now we have this tension. What's happening? Are things delocalized, because this is what we expect? Or are things localized, like the Feynman diagrams indicate, and like this picture of open strings indicates, and like we would think? And the answer is both are correct. Of course. Because there's nothing, I mean, of course, I would not tell you wrong things. Of course. Both are correct. And how do we reconcile both pictures? Do we have a string between the two? Yes, we do. This indeed becomes a string. But who told us that the string is in 4 dimensions? This from the picture you could not tell. There was nothing that told you that this surface is in 4 dimensions. Right? Maybe you assumed it in your head, but you shouldn't. Indeed, what happens is if you think that this quark and anti-quark are at the boundary of this 5-dimensional space, are at this boundary of ADS, and then there is some direction, holographic, that emerges, some z direction. And this string is going inside ADS. And it's going from a point in the boundary, goes inside the space, and comes back. Okay? But now, what do we, people in this brain, observe? If something goes inside ADS and comes back, what we see is the shadow of this object. What we see is we have a string here that is going inside ADS, and that's a nice line. But what we see is the causal cone. It's the things that affect this. It's like the shadow of it. And it's this shadow of it that gives us the illusion of these delocalized lines. So the Faraday lines are like the shadow of the 1-dimensional string that is stretching in the bulk. Okay? That is kind of the qualitative picture, of course. So these lines are like the shadow of the 5-dimensional string. Okay? So it is just a fact that if you take a point, and the point is very close to the boundary, what is its effect on the boundary? Well, it can affect some nearby points, but it's some blur. You agree? But if you take this point and carry it further and further away, it can affect now a big blur. So things that are local inside, in the bulk, they become more and more delocalized as you go further and further inside. And that's why these lines, they start very dense, and then they open up, and then they join again, precisely because what's happening is that things in the bulk are always local, but they are going inside, and as they are going inside, they describe infrared physics, and then they go back to the boundary describing again UV physics. And this I will come back to it in the next time and be a little bit more precise. But this is the basic solution to this puzzle. We do have a 1-dimensional string, but the way to perceive a 1-dimensional object as higher dimension is projecting it, if we project it into lower dimensions, and in this way we get this illusion of a higher dimensional object.
Does this mean you can think of the flux tubes when propagation of string into the bulk is penalized, so it can't really, like if the string can't go very high at z, then the shadow won't be very big and it'll look like a flux.
Absolutely.
So there's like some penalty to...
Absolutely true. That intuition is totally correct. So let me repeat a little bit what's your name?
Caleb.
What Caleb said. So what Caleb is saying is that, well, this is what happens in a conformal theory. The string likes to go inside a lot and then come back. But then this already gives us some intuition. So this happens in ADS. That's a property of ADS. Right? At some point we will probably do this exercise of asking what's the minimal surface between two lines in ADS, and we'll see it goes well inside and comes back. Okay? But you could imagine a different background. A background where the warp factor is such that it costs a lot to go inside. See? It's like if you want to run from a point here to a point here and you are inside the water. Typically you want to leave the water first, run, and then come back again, right? And now it depends on the material. If it's sometimes it might be good to do a circle, sometimes it might be good to first get away and then run, and so on. So you could imagine some background. This is what happens This kind of thing is what happens in a CFT. And in a confining theory, what will happen is that the string will go inside, but just some maximum z, and then stabilize and stay there. And this would be the typical profile for a non-CFT or a confining theory. And then when I project what this second guy will give, it will open up a little bit in the beginning, but then it will give some tube of fixed width, and then it will localize again at the end. And this is indeed what a flex tube looks like. It's some tube of energy with a fixed width. This is the picture you imagine if things are going away and then coming back, but staying at a fixed distance because it costs some energy to go inside. But if things go inside like this, then you get a more delocalized, and then you get this pattern of Faraday lines. So from the ADS5 point of view, the picture is very similar. It is just whether it goes inside a lot or not. From our point of view, it looks very different. But that's the solution to the puzzle. Yes?
So I get the analogy of like the ADS-CFT stuff, but physically speaking, you're saying like actually like the string is moving in this fifth dimension because
Yes.
we never actually specified that these lines have to be within these 4 dimensions. But these lines are gluon exchanges, like in our old picture,
Yes.
which do actually happen in like 4 dimensions and
Yes.
not 5.
Yes.
So where does this movement in the fifth dimension come from? Like, is that an actual physical movement?
You see that, first of all, if you just exchange one gluon, it's a super quantum string. So we should be careful with something. When I draw just a string, I don't say it's a classical string, right? So I'm saying it's a string, but a vibrating one. I sum over many configurations, right? When the coupling is large, it will become classical. So when the coupling is large, you should really draw one picture and just one picture. You don't need to vibrate. But then the coupling is large, so you don't have an intuition of gluons because you have to sum infinitely many. And then the gluons are no longer the relevant degrees of freedom. When you are describing weak coupling and just one gluon, then this doesn't look at all like a surface. This doesn't look like a flux tube either. So then I would not have a puzzle. I mean, I would not claim that this looks like a string. It's just a gluon being exchanged. And in fact, this is how things work. You see that the way you should expect things to work is that you should consider, say, the quark-antiquark potential. And you should compute it. And if you compute it, you should see that when the coupling is small, the physics are mostly 4-dimensional. And I can indeed interpret them by saying that I just have gluons propagating in 4 dimensions. But as I tune the coupling, this description becomes less and less and less adequate. And the extra dimension should be emergent, should appear. And then to describe the outcome of the computation at large coupling, the appropriate description would be of a string moving in 5 dimensions. Okay? So you can turn the question around, and you can say that the path integral over strings in 4 dimensions, when the strings become very quantum, they become a theory of gluons in 4 dimensions. That's equally mysterious.
Yeah.
But that's just saying that if you try to study one regime which you are not supposed to with one theory, I mean, you don't have intuition. What intuition do you have for strings that are fluffy and vibrating like crazy and so on?
But like, ontologically speaking, we're still talking about like Young-Mills fields in 4 dimensions, and they may be very quantum and may be very weird, and like the notion of particle may not necessarily make sense, but like, where does this 5th dimension come from? Like that's ontological things I don't care. I mean, it's ontological, I don't know. Ontological, like what is happening with the wave function and so on. Okay, I don't know. These are words. I don't care about words. I care about formulas and pictures. And I'm just saying that the outcome, the way to describe your result, one way of describing is I can tell, for example, you study the quark-antiquark potential, and we might do it tomorrow or maybe next week. And we find that the coupling is some gamma of 1/4 to some funny power. I have no way of explaining that funny number. And then I tell, oh, but that funny number is just the area of a minimal surface between 2 lines in antidesiter. Okay, then if you are an ontologist, you would say, oh, then perhaps there was some string. Okay. I think you should, yeah.
So can the string in the bulk, that's only used to describe gauge fields in the 4 dimension? So like what happens if like, I'm trying to think of Martine's question. What if like the gauge field like polarized vacuum, so like a photon is electron positron, then those aren't the electron positron but aren't gauge fields, so they can't really be in the bulk, right? They're actual particles. So how would you formulate like vacuum polarization in this picture?
Vacuum polarization, so let's try to make something a bit more physical. For example, vacuum polarization diagrams would appear when I consider correlation functions in my gauge theory. Right? Suppose I consider correlation 2-point function between f squared and f squared. Trace f squared with trace f squared.
Will it also contribute to the potential too, then?
To the quark-antiquark potential?
Yeah.
Yeah, they would. Yeah, they would.
Okay, so we can talk about what we've been talking about, right?
Yeah, so okay, so from that point of view, I would say that all of them are included in the string path integrals. They also contribute to the description of the flux tube, right? I mean, yeah, there is a, yeah, that's what I would say, yeah. I mean, I would not, why do you have it in mind that it should be different?
Yeah, so I guess.
So the fact that this is a gluon, or if it's a fermion loop, I don't distinguish it. I don't want to say that a flux tube is just made of gluons. A flux tube is a tube of energy made out of all the fields of your theory. Now we know that the gluons are the most important ones, but if you have fermion scalars and so on, like in n equals 4, this dot 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 contain fermions and scalars and so on, and they definitely will be in the loop. Here in this loop there can be gluons running, scalars, fermions, many things. I do not want to distinguish between the various things.
So you can't identify like some configuration of the string with a single Feynman diagram?
No. No, yeah, you can only compare physical quantities. A single Feynman diagram is not something physical. So you can say, this is how I compute a quark-antiquark potential in string theory. Here is how I compute it in gauge theory. I add up everything and then I compare. Diagram by diagram, it's not possible. So there is no example of ADS-CFT yet where we can derive, where we can really start with Feynman diagrams and rigorously try to derive the string theory. There are two examples where people believe that perhaps it should be possible, and people tried for a long time. And one example is our vector theories, which are dual to very complicated quantum gravity theories, much more complicated than ADS5 times S5. But on the other hand, the gauge theory is much simpler. And because the gauge theory is much simpler, it's like a bunch of free bosons, people believe that perhaps they could try to map diagram by diagram and try to reconstruct a string. Another example, which is perhaps more interesting, is related to the non-unitary theory of yesterday's tutorial. So, but this is some recent development of like last week or 2 weeks ago. I can tell you more about it later, where I think that there should be possible to make some progress there as well.
We get a hint of the gauge gravity growth from the open closed string reality, but it is not so apparent at the end. So
it's not so apparent. No, I mean, it's just a statement that this picture is like the open string picture, where I have degrees of freedom on the brane, which are open strings. Right? Because this is the low energy effective action for open strings. Right? You write the action for open strings, you find the string effective action on the brane, and you find the degrees of freedom. And that is kind of the closed string picture, where instead I put these objects and I see what background they deform. So it's like the graviton version of this story, right? So so we study the background generated by branes. So in one picture, you keep the branes and study the theory on the branes. The theory on the branes here is Yang-Mills. On the other case, you say, no, I want to study the background that the branes generate. And after I study the background, I ignore the branes. That's the closed string picture. More questions? Okay, so tomorrow I'll conclude with comments about ADS-CFT, why it should be true, even further evidence. We'll discuss a bit the geometry of ADS, and we'll be done with conjecturing this duality. And then next week we'll start working on the dictionary and seeing how we can use this duality for various things, and how we can check it and use it and learn new physics from this duality. Okay? Very good.